Hello, my name is Raluca Găină and I will be presenting today our first tag competition on the board game Pandemic as well as adjacent work. This is me. I finished my PhD during a pandemic in May 2021 and I'm now a year into my new job as a lecturer in Game AI at Queen Mary University of London in the UK. Today's talk will describe the game that we've targeted, Pandemic, as well as TAG, the tabletop games framework, the competition setup, sample AI player performance, and some game variations that we've built. First off, what is Pandemic? Pandemic is a cooperative board game, played with 2 to 4 players on a board which is represented by a graph of major cities in the world, such as London, Delhi, Tokyo, and Buenos Aires. This is a world where cities get progressively more infected by 4 diseases over time. Players move their pawns around the board, trying to clear disease, or they play cards from their hand to cure the disease before time runs out, or infections get too much out of control. The action space available to the players is made up of 5 types of actions: moving their pawn between adjacent cities, or flying to other cities with cards in hand, or moving between research stations on the board, building a research station in the current city with a matching city card in hand, potentially moving it from a different location if the limited supply is exhausted, treating disease, which removes a disease cube in the current city, share knowledge, which allows players to give or receive cards from other players in the same city, or discover a cure, which allows to discard 5 city cards in hand of the same color to cure the disease of the matching color. Cure disease is easier to treat, and if all diseases cured are removed from the board, the disease becomes eradicated and no new diseases of that type will appear on the board in the future. Eradication is not necessary to win. However, all 4 diseases need to be cured only. While there is only one win condition, there are 3 ways in which the players can lose. If no more cards are left in the player draw deck, the number of rounds available in the game is therefore limited. If no more disease cubes are available in the supply when more disease should be placed on the board, the players need to manage the spread of the disease. And if more than 8 outbreaks occur by oversaturating a city with disease, each city can only hold 3 disease cubes, and if more need to be placed then an outbreak occurs, and 1 cube of the same disease will be placed on each connected city. We summarize the challenges faced by AI players in Pandemic as follows. First, the game is cooperative and requires coordination between players. Each player has a large and dynamic action space available for each decision to be taken, with over 250 actions observed at a time. Further, there are many components. There is a large board with many locations, many cards and tokens, all leading to large game state spaces. As a result, the game requires effective juggling of the many things going on at once. Infections, outbreaks, managing player cards, building research stations. There will be many conflicting objectives, and making correct choices is key to success. Players take on different roles as well, and being able to maximize the use of each role and special abilities is important, as is long-term planning. Games can last for several hours for humans and involve hundreds of cooperative decisions. It is not fast or trivial to simulate games to the end. Finally, uncertainty and hidden information play a role in raising the challenge as well, in the form of the randomly shuffled face-down decks of player and infection cards. The game is very challenging for human players as well, and the game is overall considered one of the best cooperative board games in the world, with more than 5 million copies sold. So what does it take to play this game well? Well, there are two options that can be considered: whether communication is allowed between players and whether it is not. If communication is allowed, then efficient communication is important, strong group intelligence skills and strategic skills as well. If no communication is allowed, then instead coordination becomes key, strong individual strategic skills and adaptability to each other's plans. In our version of the game, there is no communication allowed. Therefore, the second case is the one that we are focused on. Pandemic was the first game implemented within the tabletop games framework. The Tabletop Games Framework, or TAG for short, is a framework developed for the study of various AI techniques in a general tabletop game setting. It is implemented in Java and supports 4 models for the use of statistical forward planning methods on a variety of games, starting from simple abstract environments like tic-tac-toe and dots and boxes to complex strategy games such as Dominion, Settlers of Catan, or Terraforming Mars. The framework includes tools for data logging, optimization of games and AI players, and video recording of gameplay as well. The pandemic implementation in TAG includes a heuristic function which is used by the sample AI players provided for evaluating game states. It is a simple linear combination of the following features with the associated weights on the screen: the number of discovered cures, the number of disease cubes remaining that are not on the board, the number of player cards remaining in the draw pile, the number of cards in the current player's hand, the number of outbreaks which have occurred in the game so far, the number of research stations on the board, and whether the player is currently at a research station or not. Because we implemented this in a digital version, we can easily change things about the game. Things like the number of cards players have in hand at one time, how fast they lose due to infection outbreaks, how fast the infection spreads around the world, and so on. This means we can make the game easier or harder. What difficulty is right? Well, the goal is to obtain automatic players competitive with humans. So we decided to run a competition with different versions of the game to crowdsource bots that directly compete with each other to be better in this cooperative setting. So, how does the TAG Pandemic competition actually work? We made several game configurations public, allowing to play variations of the original board game. Participants then submit one agent able to play variations of the game. They have 100 milliseconds per decision at every game step. We follow pandemic survival rules that we'll explain next, and offer the $500 prize for the winner, although we didn't actually end up getting any entries this year. Each bot then plays with clones of itself in 100 repetitions of each test configuration and tries to win most games the fastest and most efficiently compared to all other entries. Survival rules for Pandemic were developed for human tournaments of the game, and we adapted them for this competition. We have the same random seed for all of the games, meaning they have the same shuffle of decks and the same initial board state. The same test configurations were to be used for all entries as well. The aim of the competition is to win the most games, with several tiebreaks put in place. The game duration in number of turns, with minimum being prioritized in winning games and maximum in losing games, the maximum number of diseases cured, the minimum number of outbreaks, the minimum number of cities about to outbreak, minimum number of diseases cubes on the map, and finally the maximum number of diseases eradicated. We use 3 event cards only: Airlift, which allows you to move any pawn to any city, and Government Grant, which allows a free build of a research station. And we also used 5 player roles, with their individual abilities detailed in the paper and official game rules: the dispatcher, the medic, the operations expert, the quarantine specialist, and the scientist. How do the sample AI players do on these versions of the game, do you ask? We use 3 players in our experiments. Random, that simply makes random choices out of all available actions. One step look ahead, which simulates the effect of all available actions and picks the one that leads to the best next state. And Monte Carlo tree search, which builds a tree of statistics by simulating possible actions up to some depth in the future and picks the one that is best in the longer term, on average. Both OSLA and MCTS use the heuristic described previously to decide what makes a good state. We overall saw 0% win rate for the default and hard configurations tried, and 100% win rate for OSLA and MCTS on the easier configurations, with less cards required for curing disease, while random remains at 0%. But we looked deeper and observed different behaviors for the AI players as well. OSLA appears to favor more static card exchange playstyle, where it does not really care about leaving the starting location. All players remain together and exchange cards to maximize the chances of curing disease, without caring about the state of the world. MCTS, on the other hand, moves around the board much more, attempting to keep the disease under control. However, it uses cards for movement often, meaning it becomes less and less possible to win the game the longer it goes. The losing condition we observed to trigger most was for outbreaks, although players occasionally also ran out of cards in the player deck. Interestingly, when rules were changed, new scenarios appeared not covered in the original rule set. So what happens if the deck of cards which decide which cities get infected runs out? This cannot happen with original rules and humans trying to win. Our version of Pandemic therefore includes a 4th loss condition for when there are no more cards left in the infection deck, and we are interested in exploring these scenarios more in future work. Finally, we explored game variations in more depth. We mention here only the relevant parameter space explored for the experiments, made up of 11 parameters with possible values as shown on screen and default values highlighted. We considered the number of epidemic cards in the player deck, maximum number of outbreaks before loss, the number of city cards required to cure disease, the maximum number of cards in a player's hand, the maximum amount of disease in a city before outbreak, the number of cube tokens in the game per disease, the number of cards players draw at the end of their turn, and the role for players 0, 1, 2, and 3. The resulting search space is 48,600 for 2-player games and 1,215,000 for 4-player games. We use maplets to illuminate the pandemic game space. We start from a random solution, we run for 1,000 iterations, and we store the best solution found in a 7-dimensional behavior map. For the fitness, we use the target win rate for simulations using a 1-step look-ahead algorithm, and we tested target win rates of 100% and 50%. For the behaviors, we use the number of outbreaks that occurred in the game, the minimum number of disease cubes remaining in supply for one disease, the number of cards in the player deck, the number of cards left in the infection deck, the number of diseases cured, the number of diseases eradicated, and the total number of disease cubes on the board at the end of the game. It turned out that Maplets was only able to cover 0.18% of the whole map with 1,000 iteration budget, and it did not manage to find many variations for the disease eradication behavior. In the game, it is generally easier to win early due to more cards being available for curing disease, and the more cards get discarded, the less probable it becomes that one player will be able to gather enough of one color for a cure. However, Maplets manages to find variations where late wins are possible too. It is also possible to find balanced variations when evolving for 50% target win rate. This typically allows players to keep more cards in hand and require less for curing disease, therefore favoring OSLA's playstyle here while still keeping a challenge. We also applied the N-double bandit evolutionary algorithm, an optimization tool available in TAG, to study in-depth statistics about the parameters and find interesting synergy. Most notable in all experiments is the dominance of the scientist player role, which allows to cure disease with one less card than normally required. NTBR reveals the medic as the best partner for the scientist and the dispatcher as the worst role. Although the dispatcher is beneficial as it allows for more flexibility in movement, the AI players are not able to take advantage of its special abilities. NTBR also reveals the number of cards required for a cure as the most impactful parameter regarding game difficulty settings, and the number of cards drawn by players at the end of their turn as the least impactful parameter. It appears that if the loss conditions are difficult enough, having more time in the game does not make a difference to the player's chances of success. So we have some ongoing research questions left. The first would be, can we actually find automatically some game versions which are easier, harder, different, or more interesting for human players as well? This would allow for more people to enjoy the game and offer new challenges to players who know the game and want a fresh experience. Our results so far are biased by the performance and playstyles of the AI players tested. And also, can we get automatic players able to achieve a high level of play? Given the cooperative nature, it would allow for solo play and more people to enjoy the game as well. So, can we save the world from pandemics with AI? We are not quite there yet, even with this simulated board game, but we're hoping we'll see some exciting breakthroughs in the future. Thank you for listening.